Welcome to our Introduction to Probability Theory. Probability is a fundamental concept that helps us measure and understand uncertainty in our daily lives. We encounter uncertainty everywhere. When we flip a coin, we don't know if it will land heads or tails. Weather forecasts predict rain with certain likelihood. Rolling a die gives us one of 6 possible outcomes. Probability is expressed as a number between 0 and 1. 0 represents an impossible event that will never happen. 1 represents a certain event that will always occur. A probability of 0.5 means the event is equally likely to happen or not happen. Understanding probability helps us make informed decisions under uncertainty. It provides a mathematical framework for analyzing random events and calculating the likelihood of different outcomes. Now let's formalize our understanding with the mathematical framework of sample spaces and events. A sample space is the set of all possible outcomes of an experiment. For a coin flip, the sample space contains 2 outcomes, heads and tails. For a die roll, the sample space contains 6 outcomes, the numbers 1 through 6. Each experiment has its own unique sample space. An event is a subset of the sample space. It can be a simple event containing just one outcome, or a compound event containing multiple outcomes. We can also define the complement of an event, which includes all outcomes not in the original event. This mathematical framework allows us to precisely define and work with uncertain events. Understanding sample spaces and events is essential for calculating probabilities and solving more complex probability problems. Now we'll learn how to calculate probability using the classical probability formula. This formula applies when all outcomes are equally likely and we have a finite sample space. The formula states that probability equals the number of favorable outcomes divided by the total number of possible outcomes. This requires that all outcomes are equally likely to occur. Let's work through some examples. For a coin flip, the probability of getting heads is 1 favorable outcome divided by 2 total outcomes, which equals 1/2 or 0.5. For rolling an even number on a die, we have 3 favorable outcomes, 2, 4, and 6. With 6 total possible outcomes, the probability is 3/6, which simplifies to 1/2. Finally, when drawing a red card from a standard deck, there are 26 red cards out of 52 total cards. This gives us a probability of 26/52, which equals 1/2. The classical probability formula provides a systematic way to calculate probabilities when outcomes are equally likely. This foundation will help us tackle more complex probability problems. Probability theory is built on 3 fundamental axioms that govern how probabilities must behave mathematically. These axioms ensure consistency in all probability calculations. The first axiom states that all probabilities are non-negative. You cannot have a negative probability. The second axiom requires that the probability of the entire sample space equals 1, representing certainty. The third axiom deals with mutually exclusive events, events that cannot occur simultaneously. For such events, the probability of their union equals the sum of their individual probabilities. An important consequence of these axioms is the complement rule. The probability of an event not occurring equals 1 minus the probability of the event occurring. The complement represents all outcomes, not in the original event. These fundamental rules provide the mathematical foundation for all probability calculations. They ensure that our probability assignments are logically consistent and mathematically sound. Conditional probability introduces the concept of probability that changes based on additional information. It answers the question, what is the probability of event A, given that we know event B has occurred? The conditional probability formula is P of A given B equals P of A intersect B divided by P of B. This formula restricts our sample space to only those outcomes where B has occurred. Let's examine a weather example using a tree diagram. If we know it's cloudy, the probability of rain increases significantly. The probability of rain given cloudy skies is 0.8. Much higher than the overall probability of rain. Another example involves drawing cards. If we know a card is red, what's the probability it's an ace? There are 26 red cards total, and 2 of them are aces. So the conditional probability is 2/26, which equals 1/13. Conditional probability is fundamental to understanding how additional information affects our probability calculations. It forms the basis for more advanced concepts like independence and Bayes' theorem.